Welcome back, everyone. This is ocean acidification number 2. And if you're watching, congratulations. It's because you finished ocean acidification part 1. Okay, let's talk about the ocean. The ocean has some structure to it. And this structure is based on both the salinity, or the salt levels, and the temperature of the ocean water. Now, the surface of the ocean is the thinnest layer. This is the layer that is in contact with the atmosphere and how the carbon dioxide is actually dissolved into the ocean. It's also where the sun's energy warms the ocean, so it has the highest temperature. Beneath the surface is a transition layer, which ranges from 660 feet all the way down to 3,300 feet beneath the surface. Here, the temperature decreases with depth, and the salinity also changes. Now, because the temperature changes, we call this a thermocline. And beneath the thermocline is the deep ocean. And the deep ocean is rather cold, and the pressure is really great. And that's caused by the thermocline and the surface waters pushing down onto it. And since the atmosphere is in contact with the surface layer of the ocean, you probably already imagine that this layer contains the most carbon dioxide. And so as carbon dioxide levels in the atmosphere have risen since the industrial boom, the pH of the surface ocean waters has fallen by 0.1 pH units. Now you might be thinking, well, that's not very much. But keep in mind the pH scale is logarithmic. And so that means that this is actually a change in about 30%, increasing the acidity. And so the rise in carbon dioxide levels in the atmosphere is also believed to be the cause of global warming. And so if this greenhouse gas continues to rise in the atmosphere, then the overall temperature of the Earth will be expected to continue to rise. And so based off of the results of our last experiment, remember that hot ocean waters allowed for more outgassing. So that means even more carbon dioxide will be released into the atmosphere. Now, that's kind of good news for the ocean because it makes it less acidic, um, but remember, this will further increase the temperature of the atmosphere, which could be a bigger problem. In fact, remember, all that extra CO2 in the atmospheric reservoir is trying to find places to go to. And so this is just another elimination of a reservoir for it to go. Now, at the surface, the warmest ocean waters are at the equator because that's where we receive the most direct sunlight. And when these global surface winds move across the surface of the water, they put the surface currents into motion. So for example, in the northern hemisphere, the westerlies, they move the warm water from the Gulf of Mexico toward the cold polar waters at the North Pole along a surface current called the Gulf Stream. And you can see the warm water of the Gulf Stream in dark orange moving away from the southern latitudes toward the colder water in the north. Now, once the water reaches the north, it begins to cool and it sinks below the warmer water that's coming in from behind it. And this is how surface currents connect with the ocean currents deep in the ocean. Now, however, cool surface currents also exist. When the warm water is displaced from the equator to the cooler, uh, up to the cooler surface area, that leaves some space here left behind for the cooler surface waters to move down and replace it. And so this means that each warm surface current is accompanied on the coastline opposite of it by a cooler surface current moving toward the equator. Here it is warmed by the sun and moves along the warm surface current. And this complete cycle is known as a gyre. Okay, so when we look at the pH measurements of the surface ocean, we actually notice a pattern. The dark colors in this diagram show a pH around 8.0, while the white regions, circled by orange outline, have a measured pH of 7.5. Now the pattern here is that you can see the cool temperature surface currents in this image, right? As the white moves out in this direction, or as the white comes down along this continental side and moves towards this direction, but we don't see them over here where the warm surface currents are moving towards the north. And so remember, outgassing carbon dioxide occurs at the surface of the ocean, and it does so at a faster rate at these warmer temperatures. And so the locations with colder surface waters retain that carbon dioxide, making these surface waters more acidic, just like what we observed in that last experiment. Now, why is CO2 in the ocean actually a problem? Well, it may not be. For algae and seagrass in the ocean, they use carbon dioxide to perform photosynthesis. And so you might be thinking, great, that means molecular oxygen, O2. That's what we breathe. It's produced, which can be outgassed into the atmosphere and help humans on the surface. But there's more. It is a problem for oysters, clams, sea urchins, corals, and calcareous plankton, and also this beautiful creature that we commonly call a sea butterfly, or scientifically a pteropod. And so the sea butterfly is a major food source for small and large organisms. Take a look at the food web. Here's where the pteropods are. Imagine that every secondary, tertiary consumer needs to eat pteropods in order to survive. And so that means that humans that rely on these tertiary and secondary consumers as a food source are going to be without that. And so how are pteropods affected by carbon dioxide in the ocean? Well, let's take a look at that reaction again. Remember, carbon dioxide and water produce carbonic acid in a reversible reaction. And then carbonic acid produces hydrogen ions, which make the water acidic, and bicarbonate ions. And now there's a third reaction in this process where bicarbonate can further dissolve into a hydrogen ion and carbonate. Now, the equilibrium constant for this reaction is actually extremely small, 4.69 times 10 to the negative 11. That's extremely small. And so basically the production of carbonate never happens. And so carbonate, though, is found naturally in the ocean, and there's actually quite a bit of it. The carbonate ion is what the pteropod and also other organisms absorb into the water to make their skeletons and shells, just like the sea butterfly that I showed you in that last picture. And so, furthermore, this equilibrium constant of this reaction also tells us that when additional acidic species, so this hydrogen ion that was made back here, is now in the ocean, uh, it can react because this low K value indicates that we favor a reverse reaction. So when we add hydrogen ions, it will react with the carbonate that's in abundance in the ocean and go back to make bicarbonate. So yeah, you might be thinking, well, that doesn't make the ocean more acidic. No, but what it does is it makes the ocean lose carbonate, which is what the sea butterfly uses to make its shell. And so essentially, we're basically stopping calcification from occurring when this happens. Now, there was an experiment conducted that I call the 2100 experiment because what scientists have done is they've prepared a sample of ocean water that has the pH level and the carbonate level of what we expect ocean water to be like in 2100 if things continue down this path. And so they put a pteropod shell in this water, and you'll notice just after 45 days that shell is basically completely dissolved in a way that it couldn't sustain its life within it. Now, ocean acidification has potential economic impacts that are particularly concerning for communities that rely on fishing associated with upwelling seasons. Now, upwelling occurs along the cooler, weaker surface current, so like along the coast of California. And when the atmosphere weather patterns come through and change, they change the surface winds, and those surface winds blow the surface water in a way that makes the warm water at the surface, which is heated by the sun, move offshore. And so that leaves kind of like an absence here of water for the cold water to rise up in place, and that's what we call upwelling. And so the consequence of the upwelling of deeper, colder, or nutrient-rich water usually would increase nutrient-rich biological activity, which makes for good fishing grounds near the surface. Now, Dr. Richard Feely and his team at NOAA's Pacific Marine Environmental Laboratory conducted measurements of pH along that Pacific coastline. And this is a pH profile of one of the sample sites on their journey. Each black dot indicates a location where the apparatus collected a pH measurement of the ocean water. Now, the combination of these measurements were then mapped to make this pH profile, connecting the lines of equal pH. So all of these measurements fall within the surface zone of the ocean. And so you can see that carbon dioxide that is trapped from outgassing down in these deep ocean currents that come up during upwelling bring with them lower pH values as they rise up the continental shelf. And so that means less biological activity and less fishing. Now, historically, the average pH of the ocean was 8.2. And so since the industrial time, the average has dropped only 0.1, but remember that's quite a bit in terms of the pH scale. And so based on the current and projected levels of carbon dioxide in the atmosphere, the average pH of the ocean's surface is expected to be as low as 7.8 by the year 2100. And so this is even more of an issue for the already threatened coral reefs. In addition to the increase in temperature that currently threatens coral reefs, they also need a basic solution, carbonate-rich environment to build their skeletons in. And you can see in this diagram that the conditions for coral reefs are far less than adequate, even at a pH as low as just 7.8, which keep in mind is more of a base than the regular water that you and I interact with every day. Okay, so if you want to learn more about ocean acidification, check out the next videos that I have. And if you felt like you missed something and you need to get something more out of this video, go back and watch Ocean Acidification Part 1, where I explain the chemistry of the ocean in more detail. Also, check out these resources because you can learn a lot about ocean acidification and continue the conversation. Talk to people about this problem. That's the first step in solving it. And trust me, we can do this together. I want to thank you all for watching and have a good one.